Hey everybody, I want to talk about chapter 4. So when we're looking at chapter 4, we're looking at exercise metabolism. So let me pull up the PowerPoint, maybe. All right, what we have to think about here is how do we produce the energy? How do we recover? What does exercise end up influencing? How do we measure how much work we've done, how much fuel we'll need? So that's what we want to kind of break down here a little bit. So let's start this slideshow. Perhaps. Here we go. So we know when we move from rest, at rest, we're basically 100% aerobic, okay? We have very low blood lactate levels, and our resting O2 consumption is fairly standard. We're going to look at 0.25 liters per minute, or we're going to look at the breakdown at 3.5 milliliters per kilogram per minute, right? So at rest, that is what we aerobically look like. As we transition to exercise, that ATP production has to increase immediately. It has to turn on. So we're going to see a rapid uptake in oxygen. We're going to try and get to a steady state, an ability where we're meeting the demands in 1 to 4 minutes. Once we hit that steady state, our ATP requirement is met through aerobic APT production. So the faster we can get to steady state and our body is ready to transition from rest to activity, the more efficient we'll become. We talked about the last chapter when we looked at bioenergetics. We initially produce that ATP through anaerobic means, right? So we have the ATP, PC system, and glycolysis. We talked about the fact that there's going to be a little bit of a lag in oxygen uptake at the beginning of exercise. Even though it increases rapidly, there's going to be kind of that little pause. We're going to consider that to be our oxygen deficit. So if we start to look at a treadmill and we're looking at speed, if we go right to 7 miles per hour, our ATP and energy expenditure is going to require between 6 and 7 moles. There's going to be a lag here, and that's that oxygen deficit where it increases, but until we hit that steady state where we're a couple minutes into the activity, there's going to kind of be that grayed out deficit. That is going to be important to come back to later because we're going to have to pay back that deficit. So when we look at this initial exercise time, our PC levels will drop down. Because remember, we're going to get into them and use them in that anaerobic state, okay? So we're going to see initially a lot of that ATP production is coming from the PC system, but it's going to fall off dramatically and very quickly, okay? So, and you're going to see where that initial 10 seconds is going to be that ATP PC system, right? And then glycolysis is going to kick on. So while we see that PC system fail quickly, you're going to see that glycolysis really doesn't start to kick on until we're 30 seconds to a minute in. It's going to peak at 2 minutes and then it's going to fall off. Now, when it falls off, we should be transitioned into steady state and aerobic means. If we look at, trained versus untrained, trained subjects, generally speaking, have a much lower oxygen deficit. Why? Well, because they're aerobically conditioned to be better. So their capabilities and their capacity is better. their cardiovascular and their muscular systems have both adapted to it. So what ends up happening here is we have less production of lactate and those free hydrogens. So we get to that steady state faster and we have less of a deficit. So again, you can tell trained individuals versus completely untrained individuals, you're going to see them not necessarily have big differences in breathing capabilities as they start exercise, where you're going to see completely untrained subjects failing faster. So we know we want to get to steady state. The quicker we can get there, the more trained we tend to be. When we look at recovery from exercise, oxygen uptake remains elevated above rest during the recovery. Remember, we kind of have to repay back that deficit from the beginning, all right? They talk about this, it used to be termed that oxygen debt. Now they're going to look at that as an excess post-exercise oxygen consumption, or an EPOC. So what we're saying is probably realistically 20% of that elevated O2 is actually paying back that oxygen deficit. The rest of it is going to be to rebalance some things. You're going to find most of the time in the literature these are used interchangeably. So initially, that rapid portion of the OT debt, of the oxygen debt, is going to be to resynthesize our stores of PC. Okay, we want to replenish our muscle and our blood O2 stores. The rest of that debt that we're paying back, that slower portion, the one that lasts a little longer, is we still have increased needs of energy. Our heart rate is still up. Our breathing is still up. We're still going to have a higher body temperature. We're going to have circulating epinephrine and norepinephrine that are just still in our stream. And we have to put that lactic acid back to glucose. So all of those things are going to require a little bit more oxygen because our work, though the initial exercise portion is done, is still happening. So if we look at this, we're looking here in terms of moderate exercise versus high intensity exercise. You're going to see, that oxygen deficit is much, much bigger on that high energy. Okay, the oxygen requirement of what we need is going to be that much more. So we're going to go up and we're going to be able to exercise at that highest VO2, which is where much higher than where our moderate exercise is. But the length of time that we can sustain that level of activity is going to be less. So instead of doing an exercise that lasts, a lot versus nothing, we're going to see that EPOC last much longer to pay back what we did, because we just did so much more work initially. So where in the moderate exercise, we're going to be kind of paid back, 4 to 5 minutes after our exercise ended, we're going to be more in the neighborhood of 15 minutes paying it back on a high intensity exercise. So what we put in, what we pay out up front, we're going to have to get back on the other side. So again, why? High intensity, we're going to have a higher blood temperature. We will have completely depleted the PC stores. We're going to see more lactic acid because we're going to have lived in that anaerobic state a little longer than we wanted to. So we're going to see higher levels of epinephrine and norepinephrine circulating. So here's just a pictorial that kind of reminds you of all of the reasons why we'll have that excessive post-exercise oxygen consumption. So again, the balance, the lactate, how do we restore our oxygen stores? How do we manage our increased temperature, the increased heart rate, and the work of breathing, and still those circulating hormones? I would understand this slide fairly well and how it plays together. So we have a little closer look here. Let's talk about lactic acid. They had thought originally that the majority of the lactic acid was converted to glucose in the liver. Recently, they're going to look at the evidence of saying 70% of the lactic acid is oxidized by the cells. So the heart and skeletal muscles will actually just use it as a substrate. And 20% is going to convert back to glucose, and 10% back to amino acids. So one thing that we talk about, old school stuff is we needed to have a cool down post-exercise so that we didn't have a buildup of that lactic acid. And there's a little truth to that. We know that lactic acid is removed more rapidly from the blood if we're doing light exercise during recovery. So we want to see an optimal intensity at 30 to 40% of VO2 max so that we can be as efficient with that removal as possible. So if we look at that no exercise, you can see how those blood lactate concentrations stay much higher, much longer. So again, it does reflect on there should be some sort of cool down post-exercise, post-activity. So if we look at this take-home message, we know we have this EPOC, okay, otherwise known as oxygen debt, which is just going to be a higher consumption of oxygen above rest following exercise. It's going to have a rapid recovery and a slower portion. So just recognize that it will take a while to recover. The more intense the exercise, the longer it is. So let's talk about metabolically. What do we do? Let's look at short-term, really high intensity exercise. That first 1 to 5 seconds of exercise, we are pretty much exclusively that ATP PC system. When we're starting to try and continue longer than 5 seconds, we're going to have to start to shift towards glycolysis. When we hit activities that are that higher intensity, but at 45 seconds, we're going to be using the PC system, glycolysis, and we're going to start to kick into the aerobic. At that first minute mark, we're going to be 70% anaerobic, 30% aerobic, whereas by 2 minutes, we're going to be 50-50. When we start looking at prolonged exercise, if we're looking at activity greater than 10 minutes, then we have got to be primarily using the aerobic metabolism. If we're looking at steady state, our oxygen uptake can generally be maintained if we're submaximal, okay, below that lactate threshold. We're going to start to challenge that if it's prolonged exercise, either at a higher intensity or in a hot, humid environment. So we're going to see that upward drift in oxygen uptake over time because of that increase in blood temperature and increasing circulation of that epinephrine and non-epinephrine. So just recognize that prolonged exercise in a hot, humid environment or something at a much higher intensity are going to challenge the ability to maintain that steady state. So again, if we start to look at that first picture, we're submax, but we're hot and humid. So you're going to see a gentle kind of rise in that curve, that linear increase in oxygen. We're going to see if we're at a higher intensity in that VO2 max, that those are going to be a little bit even sharper as far as that linear progression, that drift upwards. So generally speaking, we won't be able to continue that activity as long. So basically, oxygen uptake is going to increase in a straight line until we've maximally hit our value. That VO2 max, once it's reached, we can't get more oxygen, all right? So it doesn't matter what happens to work rate. It doesn't matter what happens to effort. We've hit the max, which is our physiological ceiling. So that is basically as much oxygen as we can get delivered to the muscles. VO2 max, what affects it? Training helps, absolutely. But we're also going to see genetics play a role here. When we look at that ultra elite runner, their metabolism and how they're built, at a cellular level will give them an edge. We can have the desire and the want to be an aerobic, to be that Olympic athlete, but we don't all necessarily have the ability, okay? So when we look at those physiologic factors influencing that VO2 max, there's going to be a maximum ability of the cardiorespiratory center to deliver the oxygen to the muscles, what they can take in and what they can pump out. And then we have to look at what can the muscle actually use and produce. You know, how efficient are they? So we can train both of them, but that extra edge, you know, some of that will have to be somewhat considered to be genetically possible. So again, we can keep increasing work rate, and we'll see that VO2 continue to rise until we hit that ceiling. Okay, so it doesn't matter if we want to try and increase the work rate. We've topped out what we're able to do. The lactate threshold is that point at which the blood lactate rises. It is considered to be our anaerobic threshold. Once we start to accumulate that blood lactate at 4 millimoles per liter, you know, we know that we've reached it. When we're looking at untrained subjects, generally speaking, we're going to hit that level at 50 to 60% of VO2 max. Now, if we're trained, we're not going to see that level hit until 65 to 80% of VO2 max. So clearly, once we start hitting that lactate threshold, we're going to decrease our ability to continue at what we're trying to do. So we're going to start to see things build up, and that is going to slow the efforts. So if we can not necessarily hit that threshold until later in our activity, then the more efficient, the better we'll be. So that lactate threshold exists, and then we're going to see a pretty steep, pretty sharp increase in that blood lactate concentrations. If you work at a really fancy lab, or you are the Olympian who has the amazing training facility, you know, they can actually do blood draws while you're doing activity and pinpoint that pretty exactly. We're just going to know that untrained, we're going to hit it between that 50 and 60% versus 65 to 80% if we're trained. So what happens? Explanations for that lactate threshold. Slow muscle oxygen, hypoxia. So what happens is we start to accelerate glycolysis. So we are going to produce that NADH faster than we can get it into the mitochondria. So if that NADH is just sitting out in the cytoplasm, it's going to convert back to pyruvic acid to lactic acid. You know, we have that recruitment of fast twitch muscle fibers, which will break down skeletal muscle here later, but it's going to actually promote some lactic acid formation because of the enzymes. So, and we just can't necessarily remove that lactate from the blood as fast and as efficiently. So just remember, this is that pictorial. If we're in glycolysis and we're making that NADH, if we can't get it out fast enough, then we're going to convert it back. So these are going to be our mechanisms that influence that lactate threshold. So again, with training, do we get more efficient at removing the lactate? Do the muscles, are they able to maintain and accept the oxygen that they've gotten to maintain their levels? Why do we care? You know, that gets back to the, what does it actually do for us? You know, that lactate threshold is a predictor of performance. When we start looking at how efficient people are in their movement and their exercise, and we have an idea where their lactate threshold hits, we can plan better. So you can look at that as a marker for training intensity. If you know where that lactate threshold hits, you can choose a training heart rate level that corresponds to that. So you can challenge it, but not exhaust it. They used to say the lactate buildup was responsible for that muscle soreness. That delayed onset muscle soreness, DOMS, that occurs 24 to 48 hours following exercise. It doesn't support the claim. You know, within 60 minutes, that lactate is basically removed. And if that were the case, power athletes would have DOMS after every single workout. We know that doesn't happen. So why? What's happening? Well, there's microscopic injury to the muscle fibers, leads to inflammation, leads to soreness. You know, that old saying, you have to break it down to build it up. There's a lot of truth there. So that DOMS is not necessarily bad, but it is probably more muscle injury at the fiber level than it is this lactate threshold. How do we pick what fuel we're using? There's a lot of different ways to look at it. You know, if we look at this respiratory exchange ratio, this R factor, we're looking at CO2 versus O2. So if we have an R factor of 0.7, we are using fat. If we have an R factor equal to 1, we're going to use glucose, okay, or carbs. So let's just keep that in mind. R at 0.7 will be fat. R at 1.0 will be carbs. So if we start to look at this, you know, we can kind of get an idea, fat consumption versus carb consumption and where we are. So if they're measuring that respiratory exchange ratio, we know kind of what fuel we're getting into. So it's basically that ratio of carbon dioxide produced to oxygen consumed, all right? And again, it's just a way for us to start to estimate and look at, you know, what are we metabolizing? You know, what is our goal? You know, if your goal is fat burning and weight loss, you know, we need to make sure that we're in the range of intensity that allows for that. So when we look at it, and again, from a nutrition point of view, you've studied this more than what we'll go over. You know, there's about a 6% difference between fuels when we look at calories expended. So if we're looking at a lower intensity exercise, less than 30% of VO2 max, fat is primarily going to be our fuel. Higher intensity exercise, greater than 70% VO2 max, carbs are probably going to be primarily our fuel. You know, there's going to be a crossover concept. We're going to have to shift from carbs as our exercise intensity increases. Why? Well, part of it's going to be the recruitment of fast muscle fibers. Part of it is going to be levels of epinephrine. So if we look at it here, yes, we're not necessarily burning as many carbs at a lower VO2 max, but fat will start to fall off there. So it kind of gives you just a picture of that crossover concept. Here's a little clinical application to throw in here. Individuals with this McArdle syndrome cannot synthesize the muscle enzyme phosphorylase because of a gene mutation. So it cannot break down muscle glycogen. So what happens are these patients don't produce lactate during incremental exercise. They are going to poorly tolerate exercise and have a lot of muscle pain because they can't produce that lactate, which, though not common, I swear I've met a lot of kids who complain of exercise intolerance and muscle pain. So let's talk about workload. If we want to burn fat, okay, we have to look at, yes, lower exercise intensity burns more fat. But, this is the big but, the total energy expenditure is low. So our fat oxidation will be low as well. High intensity exercises, greater than, you know, around that 60% VO2 max, we only have a third of it coming from fat. and we have, 66% coming from carbs, but our total energy expenditure is higher. So our fat oxidation will also be higher. So what we want to look at is fat, utilizing fat primarily as a fuel. Our highest rate of fat oxidation is going to happen just before that lactate threshold. So again, when we're prescribing exercises, we have to understand what we're prescribing them for. And having something as weight loss as a goal, we need to have them working out at a heart rate that's going to be just below that lactic threshold. If we remember, in untrained subjects, that's going to be around 50 to 60% of VO2. So when we're looking at it, we want that sweet spot, 50 to 60% of VO2 max for an intensity is going to give us the most fat oxidation, okay? Once we start to go up over 60, we're going to see it fall off pretty quick because carbs are going to step in. But still, we want to maintain time at that 50 to 60% VO2 max. So prolonged low intensity exercise, we're going to shift from that carb towards fat metabolism because we're going to maintain it. And why is that happening? We're going to have an increased rate of lipolysis. So we're going to break down those triglycerides into glycerol and free fatty acids. And part of that is because of those rising levels of epinephrine. Excuse me. So if we are going to see this shift, initially, as time goes on, we're going to deplete that carb faster than we're going to deplete the fat. So if we can maintain exercise for longer, especially in that 50 to 60%, we're going to see that as we burn through those carbs, we really stay in that fat oxidation. So, truly, where do we want to live is that, 60 to 100 minute mark. So fats burn in the flame of carbs. We know that as we deplete our pyruvate and glycolysis and that production, we don't have as much to feed the Krebs cycle. So we have to get into that fat oxidation so that it can feed Krebs cycle and we can keep going. So once that glycogen is depleted, we get to burn up more of that fat to use as a fuel. So why do we get tired? As we deplete the muscle and the blood carbs, we're going to see some fatigue. Will ingesting carbs improve performance? Yeah, some maximally, and in long duration exercise it will. You're going to need between 30 and 60 grams of carbs per hour. You may also see some improvement in shorter high intensity exercises and activities and that 45-minute duration. So where do our carbs come from? Muscle glycogen. We're going to see that as a primary source of carbs during the high intensity exercise and what supplies exercise in that first hour. Blood glucose is going to come from the liver and glycogenolysis. It's probably going to be the primary carb during low intensity exercise. And it's also going to be very important when we look at long duration exercise. As the muscle glycogen levels decrease, we're going to need that blood glucose level to maintain. When we look at fats, intermuscular triglycerides are going to be the primary source during high intensity exercise. Our plasma free fatty acids are going to play more of a role in that low intensity exercise. So we remember FFAs are converted to acetyl-CoA and enter the citric acid cycle. They're going to also become more important when the muscle triglyceride levels start to decline over that longer duration. So keep that in mind. Those plasma FFAs are going to be really important. So here's just another pictorial. So if we look at exercise intensity across the bottom, you're going to see, that muscle triglycerides are going to play the role, a bigger role at that 65% VO2 max. You're going to see the plasma FFAs play a huge role when we're down in that 25% VO2 max category. Whereas if we shift up to 85% VO2 max, you're going to see muscle glycogen play a huge role and the ability to meet the needs. They're going to be the fuel that's selected. So here's just another pictorial when we start looking at what kind of energy we're expending over time. So you're going to see that, that muscle glycogen falls off. You're going to see blood glucose maintain through the duration. You're going to see an increase over time on the reliance of the plasma FFAs, whereas there's going to be less muscle triglycerides the longer the activity goes. So, quantifying our body fuel stores, there's going to be a what do we take in versus what we are looking for. So, give you some levels. When we look at protein during exercise, we remember that it contributes only 2% to the total energy production during exercise. It may kick up much later. When we're on a very prolonged duration exercise, maybe it'll contribute 5 to 10% later. We might see enzymes, proteinases that are activated in long-term exercise that start to allow protein to be any sort of source. The protein's broken down into amino acids, so the muscle can directly metabolize them. The liver can work on converting to glucose. But again, during exercise, protein is not going to be our choice. We know that lactate can be a fuel source during exercise. The skeletal and the heart muscle can use it and convert it back into that acetylCoA and Krebs cycle. It can be converted to glucose in the liver through the Cori cycle, and it can shuttle from one tissue and transport to another as necessary. So lactate can be a fuel source. When we look at this Cori cycle, we know lactate produced by skeletal muscle is transported to the liver. The liver then converts it to glucose. The glucose is then transported back to the muscle and used as a fuel. So it can help. So just kind of here's the pictorial. It comes from the muscle, goes to the liver, and is converted back into glucose, which then can go back and feed the muscle again. So not quite as bad. So sorry, there's nowhere to sit in my house where the picture isn't terrible. Fuel choices, it's going to be something to consider. When we look at exercise physiology, at the end of the day, we're looking at if we had to prescribe exercise, what are we prescribing and why are we prescribing it? So again, it gives you an idea why you might choose a bike or a treadmill activity for someone whose goal is weight loss, and have an idea of how hard you want them to work, because we want them to metabolize the fat, but we want to be able to challenge that aerobic capabilities. So understanding why we give people different training heart rates, this is why. This is part of why, I guess. So that is chapter 4. I'll see you again in chapter 5. Actually, you won't see me in chapter 5. I am going to try and do it just audio clips. My least favorite chapters are 3 and 5. So you don't need to see my face because I'm sure I'm making lots of weird ones as I talk. So Chapter 5's next.